Okay, next we will jump to the new chapter. We will discuss the multiple integral. As we said before, this class is about calculus. In other words, we need to discuss differentiation and integration. So far, we only deal with differentiation. Now we are going to talk about integration. And after we do the general method of integration, next chapter we will combine these two to do some generalization for the fundamental theorem of calculus. In other words, we want to generalize the Newton-Leibniz rule and find some distinguished method to compute the quantities you will have in physics, computer science, statistics, engineering, and biology, chemistry, whatever. So those are universal theorems. Okay, now first, let's recall what is integral in 1D. There are many equivalent definitions for integration. This is definite integral. And so we can interpret this as the area underneath the graph. So suppose this is x-axis, this is y-axis, and this is a graph. Okay, so the area and the graph. And if we want a rigorous definition, then we will need to compute the area. And so usually what we do is cut the region into pieces and approximate each piece by rectangles. This method actually already known to the ancient Greeks, and so approximately equals summation of the Riemann sums. So I will explain to you. So this is the length for this rectangle. The size of this rectangle is delta xi, and then the height, if you choose a point, so you can take the height fxi star as the height of the small rectangle, and here xi is in between. This is within this interval. It's within this interval. Okay, and take the limit. In other words, we cut the interval into smaller and smaller pieces. We can thus define the integral as the following limit. Actually, you will notice this is area of each rectangles. Okay, this is almost rigorous. If you need the rigorous definition, I refer you to the mathematical analysis class. Okay, and similarly in 2D, suppose we want to generalize integral, then naturally we can write down this simple. Suppose you have function over a region and you want to call something, you want to attach something similar to integral to this situation. Then the geometric side, on the geometric side, you can draw a graph. Sorry. The function and sorry. Okay. And suppose this is your rectangle, and then you can interpret the integral as a volume underneath your graph. This is a similar interpretation as 1D, as what we did in 1D. Okay, next we want to compute this guy. So first look at the base. This is which is a rectangle, and to compute it, we just cut it into smaller pieces. But here, instead of cutting along one side, you need to cut along two sides. Right, and since you have x and y as a coordinates for the base, then you may have dx1, dx2, dxi, dxn for the length of each small rectangle, the size of each small rectangle along the x-axis, and then delta y1, delta y2, blah blah, delta ym, delta yj. So each delta yj is the length for the size of a small rectangle along the y direction. And then if you do this cutting, for the base, then you can approximate the three-dimensional solid by the rectangulars. In other words, this approximately equals summation I from 1 to n, j from 1 to m. So by this notation, you're summing over all these small rectangles. And for each one, since you have a three-dimensional rectangle then you will have the volume for that is delta xi times delta yj times the height. So the height is given by the value of function approximated at some point at this point. So ij. Okay, then if we take the limit, we can define the integral to be a similar Riemann sum. Sorry. F x I y star ij star and delta a summation. So where delta a is the area for the base, which is given by delta xi times delta yj ij. Okay, so this is a rigorous definition, almost rigorous definition for 3D integral, and you can do the same thing for a 2D integral. You can do the same thing for 3D and any dimension, and there's no big difference. Now, before we introduce systematic method to compute the integral, we first give an example which can be solved using the geometric interpretation. So suppose R is a domain given by the following conditions. So it's in 2D, and x is between -1, 1, and y is between -2, 2. Evaluated. The integral so remember the notation. Here dA just means dx dy when you don't want to specify the coordinates. Okay, first let's draw the graph for this integral for the function. So let f equals square root 1 minus x squared. And what is a graph? So or z equals square root 1 minus x squared. Then it's given by, the graph is given by z squared plus x squared equals 1. So you would have this. In my bad drawing, sorry. And also extend to the negative y direction. So it's a circular cylinder, half of the circular cylinder. So if we make up the other half, then we would have this. Okay, then the integral can be interpreted as 1/2 of the volume of the circular cylinder. And recall, the volume of circular cylinder is given by pi r squared times h. So where r from this picture is given by this, or is given by this one. So this also recall this is x, y. So this is given by this condition. So r is 1. And what is h? H is given by this. So h is 2 minus -2, which is 4. So here you have 2, here you have -2, here -1, here is. Yeah, I would like to write down the coordinates for this side. Okay, then you know the integral is given by half volume, so it's 2 pi. Okay, so this is an example where you don't need a systematic method to solve the integral. We just use geometric interpretation. But in general, this we rarely have this case. Usually we need heavy computation. So next we are going to introduce the systematic method. So first we will introduce the so-called iterated integrals. The idea is similar to what we did for differentiation. Whenever you have high dimensional problem, you always want to reduce it to a lower dimension, to a lower dimensional case. So this is well explained by the following Fubini theorem. So if f is continuous function on the rectangle AB cross CD, then integral of f over the region R can be computed in the following way. You first integrate f with respect to y from C to D for fixed x. Then this will be a function of x. Therefore, next, you can integrate this function with respect to x. So notice that each step we are only integrating a one variable function. So for this one, fix y. And for this one, you get a function depending only on x. Okay, and there's no reason why you treat x and y differently. Therefore, you can reverse the order. You first integrate f with respect to x. Okay, and then you, from A to B, then you integrate with respect to y from C to D. And similarly, this will be a function. So after integration, once you get a function of y and then integrate this with respect to y. Okay, we will not give the proof here, but we would like to give some example to illustrate the method. So let's compute the following integrations. So remember that here we always use the following convention. We pair up the integral symbol to the nearest dy or dx. So this is paired. In other words, 0 and 2 is the region for y. And then we pair the next symbol with the next dx. So this is paired. Okay, so this is the usual convention. And similarly for b, so we introduce the problem b. This is given by this. And similarly, we have the following pairing. Okay. Now the solution is easy. So suppose we have problem A, then we need to use Fubini theorem. So we just integrate first with respect to y, and you keep x. So inside, what do you have? You have x squared. Here x is a constant. X squared y squared divided by 2, evaluated at 2 endpoints. Okay, then inside, what do you have? You have 2x squared minus 1/2 x squared. You have 3/2 x squared. And then what do you have? So next you integrate with respect to x, evaluate at 3 and 0. So finally you have 1/2 times 3 cubed, 27/2. Of course, you can we can integrate x first. We will discuss this extensively later when it's necessary. Here, I think there's no difference to derive the answer. And the b, the natural order, is integration 1 to first, and then 0, 3, x squared y, and dx, dy, and you have 1, 2, inside you have x cubed y, 3, 3, 0, dy. This is 27 y divided by 3 and 1, 2 dy, and then 27 divided by 3 y squared divided by 2 to 1. So actually this is 27/2. Oh, sorry. Actually this already is integration. X first. You change the order. And remark here, the theorem says the two methods should give you the same answer, which is the case here. Okay, next, let's look at the following example. Suppose you have function x minus 3y squared. What is the integral of the domain 0 to 1, 2? We just write down the integral. So here the difference is you need to write down the iterated integral by yourself. So here 0, 2 is for x, 1, 2 is for y. Okay, so I just follow the nature order. We first do this one, and then you have xy minus y cubed. Evaluate at 2, 1. You be careful. This is for y. The boundary points are for y, and then you have 0 to dx 2y minus y cubed. So 2x minus 8 minus x minus 1. So this is 0 to dx x minus 7. And then you have x squared divided by 2 minus 7x to 0. So what is the answer? This is 4 divided by 2 minus 7 times 2. So it's negative 12. Okay. Next, we will discuss the following example. Above example shows the order doesn't really matter when evaluate the integral, but the following example shows contrary. Suppose you have an integral of function y sine xy over the region 1 to 0 pi. What is the answer? So here we write down the integral as 0 pi. We first do x integral from 1 to 2. And then we do y integral from 0 to pi. Then inside, notice that this is a chain rule. So the antiderivative for this guy is negative cosine xy, and then you evaluate as 2 and 1. So dy, you have cosine y minus cosine 2y, and then you have sine y minus 1/2 sine 2y. Evaluate at pi and 0, which is 0. And the remark, if we do y integral first, then we will get stuck because you don't know how to integrate this guy. Do integration by parts, you don't really actually you can solve this, but probably, yeah, I will show you, but probably you spend more time, so it's not get stuck. Just harder. Okay, so we first let's change the order integration from 0 to pi, from 1 to 2. 1, 2, 2, and 1, 2, 2 is for x. The sine xy is dy. Okay, then 1, 2 dx. Inside, we integration by parts. Y negative cosine xy divided by x. And then, because the derivative of this guy whose derivative is sine xy. So that's how we apply integration by parts. Of course, here is with respect to y. Okay, then next on this side you will have minus integration 0 to pi, and you take derivative of y. You have 1, so negative cosine xy divided by x dy. Okay, so here you have 0 pi, and then you plug in, you have this is for y. And if you plug in y equals 0, you have nothing. When you plug in y equals pi, you have pi times cosine pi x divided by x. Okay, and then next part you have plus. So here, what is the integral here? So you have to integrate this guy, and then you have sine xy divided by x squared, pi, and 0. Okay, when you plug in, so what do you have? You have pi cosine pi x divided by x plus, when you plug in pi, you have sine pi x divided by x squared, and plug in 0, you have 0. Okay, finally you need to integrate this guy. But then we get stuck. Let's see if we can have some simple way to get around it. Yeah, I will leave it to you. It might be the case that for some problem, if you change the order or integration, then something can be solved will be unaccessible. Okay, due to time, I will not discuss this anymore. And since you already have one method to solve it. Okay, next, let's look at the following example. So find the volume of the solid S that is bounded by the elliptic paraboloid x squared plus 2y squared plus z equals 16. The planes x equals 2 and y equals 2, and the 3 coordinate planes. So solution. So here we need to interpret this geometrical problem as some integral, and then try to solve the integral by iterated integrals. So first, let's view this as a graph of function f equals 16 minus x squared minus 2y squared. And then the domain is 0, 2 cross 0, 2. So if we draw x, y, z, x, y, z, and the graph probably looks like this. Sorry. Sorry about my bad drawing. Okay, this is a picture. Basically looks like this, and then you can check that this piece is strictly about the xy plane. Okay, then we have the volume of S can be given by, recall the geometric interpretation of the integral inversely, because this graph is given by xy, fxy. Then we can write down this as integral of fxy dA. In other words, we have 0 to, so now in other words, we write down as iterated integrals as following: dx, dy, and then inside you have 16 minus x squared minus 2y squared. Okay, now let's integrate one by one. We first do this one, then we have 16y minus x squared y minus 2/3 y cubed, evaluated at 2 and 0, and then dx 32 minus 2x squared minus 16 over 3. And when you plug in 0, you have nothing. And then you need to evaluate this one, and then you can simplify a little bit. 18 over 3 minus 2x squared dx. Okay, so here you have 18 over 3x minus 2/3 x cubed, evaluated at 2 and 0. Okay, then you have this minus 16 over 3. Totally you have 48. And it's quite often you need to go back and forth between the geometric interpretation of the volume and the numerical integral. In other words, you need to go back and forth in between this one and this one. For this one, the advantage for this one is we have certain systematic method to solve it. And the advantage for this one is it's more closely related to the real problem you have. Okay, this is a good application for the iterated integral. Next, we introduce another technique. Suppose you have the following integral over the domain R. The function is sine x cosine y, and the domain is 0 pi over 2 times 0 pi over 2. And if you look at carefully, then you will notice that there are two functions, there are two factors. Each of them is a function depending only on one variable. Okay, then we have the following technique for this problem. We still write down as iterated integral, but now here this is a constant. You can move it out. And also the remaining part after integration is a constant. Okay, then totally you will have the following formula for integral. You can separate the integral into two parts and then do the product. Note that this only works for certain special domains, so I should make a remark, works for certain certain functions with special forms and certain product domains. Okay, and next we will discuss double integral over general domains, general regions. But before that, let's recall the following definition. We will not use it extensively in this class, but it's quite useful in your physics class, chemistry class, engineering class, or whatever. So it's called average value of some function in certain region. So by definition, this is given by 1 over the area and times the integral. And a remark is, if you know the discrete version, I will not tell you what is discrete version exactly mean, but if you have interest, you can search online Wikipedia, which is called direct measure. Can give the following usual definition of average. So suppose you have points A1 up to AM, so the average is given by 1 over n A1, summation from A1 to AM. It can be included in this definition, but I will not give the definition here. Okay, next, let's discuss more on the double integrals over general regions. I don't know if you noted that previous discussion only consider the regions where consider the rectangular regions. So now we want to discuss the following region. And if we write down the definition explicitly, D is given by the following conditions. X, if you look at X, so X is between A and B, and just like a rectangle region. But Y here, for each fixed X, you will have different regions for Y. Okay, so it's given by two functions of X okay, and if we write down the integral, so here we will focus on the region instead of function. The function can be taken as any reasonable functions. So suppose this, and then you can write down as iterated integrals, but we prefer in the following form according to the shape of the domain. For X, you just pick it from A to B arbitrarily. And then for Y, the boundary point depends on the value of X. So the difference between this integral with the previous examples lies in the fact that now the boundary point is vary and depending on X. And the remark these points depend on X but not on Y. This is essential. Okay, similarly, if we change the place of X and Y, then we might have the following example. So the domain D now is given by the following is given as the following domain. So Y is between C and D. And for each fixed Y, X is between H1Y and H2Y. And therefore, the integral has a nature representation as an iterated integral as follows. You integrate x first from h1 to h2, and then you integrate y from c to d. Okay, so this is the first part for this lecture, and then I will upload next two parts for this week.